Nuclear energy, vanguard of a brighter tomorrow, or harbinger of our own doom. Dun, dun, dun. Actually, somewhere in between these two. And so let's back up and imagine we have a banana. Now this banana is radioactive. In fact, this banana is so radioactive that consuming just this one banana would expose you to more radiation than living for a year next to San Onofre. Where did we get this banana? Was it from Japan? Did we irradiate it ourselves? Is it a government conspiracy to track our movements? No. No, friends. This is an ordinary banana, and the radioactivity comes from potassium. How much radioactivity is in this banana? 0.1 microsieverts. How much would you receive living next to San Onofre? 0.09 microsieverts. You see, radiation is a natural part of all life. Does this mean, though, that radiation is good for us? Not all the time. And so in this speech, I aim to dispel some of the rumors and irrational fears that we have about radiation. First, I'm going to explain how we measure radiation exposed to humans, the process of sieverts. Then I'm going to discuss how a nuclear reactor works. And finally, we're going to discuss what happened at the Fukushima plant. So moving into my first point, we have sieverts. And we already got exposed to one of these with the banana example. Now, sieverts are calculated by these equations. Thank you. What does this alphabet soup filled with sigmas mean? Basically, H shows us how much radiation is absorbed by a human body. This measurement gives us a consistent, across-the-board form of measuring types of radiation and exposure levels. What do some of these numbers mean? How can we relate these to our day-to-day lives? Well, we already got the example of a banana at 0.01 microsieverts. How much would you receive for a typical X-ray? Well, that is 20 microsieverts. A transcontinental flight going Los Angeles to LA, 40 microsieverts of radiation. How about living in a brick, stone, or concrete house for a year, 70 microsieverts of radiation? Then we start to get up into millisieverts of radiation, which is 1,000 microsieverts. Chest CT, that's 5.8 microsieverts, or 5,800 microsieverts. Then we start to move up into actual sieverts themselves. Where do we get sick? 0.4 sieverts, 400 millisieverts, or 400,000 microsieverts. That's 400,000 bananas for a single chest CT scan. That's when we start to feel sick. How much until we die of radiation poisoning? There is no cure. We are dead. 8 sieverts. Where does Fukushima lie on this spectrum? Quite low, actually. Less than the CT scan that we received at 4.2 microsieverts, or 4,200 bananas. This is for 1 day of exposure anywhere within the radiation sites of Fukushima. Not a lot for our year consumption. Let's transition what we know about sieverts and put it into the process of a reactor. How does a reactor work? Let's step back and imagine a stadium. And the entire field is covered in mousetraps. And on each of those mousetraps is a white ping pong ball. And if one of those mousetraps were to go off, the ping pong ball would fly into the air. Now you have a ping pong ball in your hand, and you just toss it into the stadium. And that ping pong ball sets off one of the mousetraps, which releases its own ping pong ball. Then those 2 ping pong balls set off 2 more mousetraps, and now you have 4 ping pong balls flying around, and this goes exponentially until you have hundreds of ping pong balls bouncing around, and then thousands. This is essentially the process of fission. An atom releases a particle which strikes another atom, releasing its particle. This process, when left unchecked, gives us the most devastating weapon in human history. When carefully monitored, gives us an exponentially huge power source for the size of fuel required. Now, when these ping pong balls are released, they create heat, measured in joules. This heat is transferred to water, which excites and turns into steam, the process of boiling, which then turns a turbine. Now, if we have it under control, then how does this lead to a meltdown like we saw at Fukushima? Well, Fukushima was not a meltdown. In fact, Fukushima was one of the greatest triumphs of nuclear energy. We have faced too long the specter of if it goes bad, and it all goes to hell. In fact, no. Fukushima, with the earthquake struck, immediately went down into lockdown. Control rods slammed into the reactor, sustaining the nuclear reaction and creating homeostasis within the core. Then the backup generators came on to maintain power to pumps, which moved a water and oil-based lubricant throughout the system in order to maintain coolant. When those were wiped out by the tsunami that then followed, the third redundancies, batteries, maintained cooling. It wasn't until a failure of humans to move additional batteries into the plant and maintain power that we saw a decrease in the water surrounding the reactor and the coolant pools. Now, these coolant pools store spent nuclear energy. Eventually, this water started to turn into steam, and that is what the Fukushima employees had to release, was the secondary and tertiary radiation from the coolant, composing largely of alpha and beta radiation, a lower form of radiation that can be easily stopped into the atmosphere. Now, the serious radiation doses that we got of gamma radiation from the plant came when seawater had to be brought in because the water level was dipping below the storage rods. When this happens, they can start to melt. Seawater was brought in, and it's actually the seawater containing salt that became broken down into gamma radiation. I feel like I'm moving so fast. This gamma radiation is what gave us the largest amount of fallout from the reactor. Should we be afraid of this? Is nuclear energy something that we need to be terrified of? Not at all. This is a major incident, but one that has been handled with extreme care and diligence. There will be very little side effects from the reactor. There will be very little side effects from the people who live around it. There will be very little side effects to us, negligible. We will see more radiation from anything that I've explained before than we would receive from winds blowing from Japan across the Pacific Ocean to us. In this speech, I hope I have dispelled some of the irrational fears that we all possess about radiation and have illuminated the future of nuclear energy. I've discussed what a sievert is, and I hope you can all understand that and take it into context in the outside world. I've shown how a reaction occurs and how fission works, and I've also discussed what happened at the Fukushima plant. Thank you for your time. This has been quite illuminating. Have a nice day.